Yep.
Okay, you probably see something on your screen saying that it is being recorded now.
Okay, thank you.
Great, awesome. Well, welcome everyone to the first Insigneo Seminar of this year. I hope you had a good break. I definitely had a long one. It was good too. And so it's great to have today, and I'm sure you're as excited as me to have Dr. Jordi Alastruey today, our speaker from King's College. His talk is titled In Silico Pulse Wave Databases for Hemodynamic Studies. And this is out of his research interest, which is on pulse wave signals and using them to create databases of blood flow, essentially. With that, welcome, Jordi, and please go ahead whenever you are ready.
Thank you so much, Inaki, for the invitation and introduction. And also would like to thank Alberto for also inviting me to give this seminar. I'm really delighted to give this presentation on in silico pulse wave signals and their relevance really for hemodynamic studies. Let me start by saying a few words about the pulse wave signal. So the pulse wave signal is the result of the beating heart interacting with flexible arteries. And when the heart injects blood into the aortic wall distends, and this distension propagates throughout the aorta and all the main arteries of the human body as a wave that we call the pulse wave. And this wave, as it propagates, it produces changes in physical properties.
Sorry if I'm interrupting. Do you mean to change your screen? Because currently it's the first screen. Still the first screen is showing up.
Oh, it's frozen? Okay.
Yes.
Before it was working.
Yes, indeed it was. It was working just now, wasn't it?
Okay, I'll try again. So, share screen. I'm sharing my screen now, I think.
Yes.
So I'll stop. And I'll share the screen. Is it working now?
Yes, yes, perfect. I'm sorry about that.
Can you see the?
Yes, I can see the beating heart clearly.
No worries. Can you see my second slide? So the movie?
Yes.
Okay. So thank you. Apologies for that. So I was talking about the pulse wave. So this pulse wave, as it propagates, it produces changes in blood pressure, blood flow, and cross-sectional area throughout all the arteries of the human body. For example, it produces the pulse that we can feel on our wrist. And there is lots of in vivo evidence of the existence of this pulse wave. So for example, if we look at in vivo data measured in rabbits throughout the aorta of the rabbit, we can see really that there is a time delay in the arrival of the foot of the pressure measurement, pressure recordings at different points throughout the aorta. And also then you can see that in mid-systole and later in systole, there is the effect of reflections of the reflected pulse wave coming back to the heart. And also the pulse wave can be observed if we take measurements using magnetic resonance imaging throughout the aorta. For example, that's the 5 cross sections that you can see on the left. And we take measurements of flow rate with time, cross-sectional area with time. We can really see again a propagation, right, of the pulse wave and the effect that has on physical properties of blood flow. So now the question is, why do we want to model pulse wave propagation and do pulse wave analysis? So we want to do that because the pulse wave can be measured in vivo using a variety of devices, including wearable devices. And it is influenced by the heart, the vasculature, the respiratory system, and the autonomic nervous system. So that makes pulse wave signals a rich source of information to assess human health, including cardiovascular health. So this is the outline of my presentation. So first I'm going to talk about how we can simulate pulse wave propagation and the effect that has on blood pressure, blood flow, etc. And then I'm going to focus on how we can create in silico pulse wave datasets and finally on clinically relevant applications of using in silico pulse wave signals. So let's start with how we can model pulse wave propagation in the cardiovascular system.
Sorry, Jordi, I think
yes,
frozen again. I'm really sorry. I don't know why this is happening, because right now I can see the screen which says pulse wave analysis Y. It's probably not the one that you are.
No, it's not.
What we could do alternatively is if you could maybe send me by email the presentation. I can try it from here because I'm not sure exactly why this is happening.
It's not a PowerPoint presentation, I'm afraid. I could send it to you, but it's not.
All right. Okay, then it will probably not work because I'm using a Windows machine. Another alternative is you could share the file if it is so there's something called there's only PDF and PowerPoints that can be uploaded.
Let me think. So I'll stop and try again. Probably because they are movies, and there might be a problem with the movies.
Sorry for that interruption. But I thought it was not the same correct slide that you were speaking from, so I interrupted.
Yeah. So now, can you see the slide?
I can see yes, videos on the 1D and the 3D model.
Okay, so I think this is the last movie that I have, or the last slide with movies, so perhaps it's gonna work better from now on. Apologies for that, otherwise I can send you a PDF of the remaining of the presentation. So I was talking about how we can simulate so in silico pulse wave signals. And when it comes to blood flow modeling, there are basically three main approaches. So there are three-dimensional models, one-dimensional models, and zero-dimensional models. So the main difference, so it's in the number, right? So 3D, it means that we account for the three-dimensional variability, right, of blood pressure, blood flow. 1D only for variation along the axis of arteries, and 0D models are space independent. So 3D models really can simulate local features of blood flow very well, but at a very high computational cost, whereas 0D models on the other extreme, they are computationally inexpensive, so we can even get analytical solutions, but obviously they provide more global features rather than local features of blood flow. And in between, we have 1D models, which are a good compromise between accuracy and computational cost. So I'm now changing to the next slide. Can you see the next slide?
No, not yet. We're still on arterial blood flow modeling slide.
I should click a bit earlier, perhaps, when changing the slide. So can you see it?
Not yet, actually. I cannot see it from my side.
Okay. So,
yes. Okay. Now that we, of course, yeah, I see the screen now.
Yeah.
It just the change is not didn't work.
Can you see it now?
Perfect. Yeah.
Okay. So now I'm going to focus on how to use 1D modeling to simulate blood flow and pulse wave signals. So in the 1D formulation, we basically so we do a domain decomposition. So if we have the whole arterial network, so we focus on one arterial segment at a time. And for that arterial segment, we describe so blood flow, blood pressure, and cross-sectional area as a function of the axial direction along the arterial segment, and also the geometry of the segment and the material properties. And then using physical principles of conservation of mass and conservation of linear momentum, we can write down really a system of partial differential equations that also includes a third equation, a third governing equation, which is tube law, which is the relationship between changes in blood pressure and changes in cross-sectional area, taking into account the mechanical properties of the arterial wall. So we can solve this system of equations numerically using a numerical scheme, and then we can actually join different arterial segments to each other through arterial junctions by solving an arterial junction problem. And the way to do that is, again, by enforcing physical principles of conservation of mass and conservation of energy. And then we need to prescribe inflow and outflow boundary conditions. So the inflow boundary condition, the typical inflow boundary condition that we use in 1D modeling is the blood flow measured at the ascending aorta. We can measure that, for example, by ultrasound, Doppler ultrasound, or by phase contrast magnetic resonance imaging. And then as for the outflow boundary conditions, so we need to account at each terminal vessel of the 1D arterial network, we need to account for the effect of peripheral vasculature, so for the resistance and also to some extent the compliance or flexibility of downstream arterial segments. And we do that through these zero-dimensional or lamp parameter models that basically have compliance and resistance as parameters. So this is, in brief, the 1D model, so the 1D formulation. So it's the 1D 0D approach that we take to simulate in silico pulse wave signals. And now the next question is really how accurate is this set of equations and this formulation, given all the number of assumptions that we are taking. So how accurate is this when it comes to simulate pulse wave propagation and the effect that has on pressure and flow waveforms? So we have done really lots of testing on how to test, basically verify that the solution provided by 1D modeling is somehow accurate compared to first experimental data. So hopefully you can see there's a movie here. I think this is the last one. I don't know if you can see it.
Apologies for
you can see it.
It's not that slide perhaps. So I'm in the 1D governing equation slide.
Yeah. So still 1D equation. Okay.
Yes.
You didn't see the boundary conditions.
No, perhaps I don't think so.
Okay, so I think it's better if you don't mind if I send you the PDF.
Sure, of course. Sorry about that. Usually doesn't
so,
works with
sorry,
the screen
I'm gonna. Yeah. Okay, I'm gonna just do it as fast as I can. Okay. So. Okay, I'll email it to you. Apologies for this.
It's my fault.
It would be much better to be in person, right? Now it's when you wish to be there in person. Okay, so I'll send you the PDF now.
I'll refresh my email. It should be here.
Okay, it has gone now.
Just refreshing my email and it should be here in a moment. Sorry about that. And Jordi, you could just tell me like next slide when to progress it, and I would be able to
Number
move it from
14,
here.
please. Number 14.
Yes, I'm still not received the email. I'm just waiting for the email to come through, and to start with number 14.
Yeah, I think so. Yeah. 15.
Oh, I have received it. Okay, and let me open the slide. I can already show it from here. So page number 14 is what we should go, right?
Yes, please.
Sure. Okay, so I will zoom it so that it takes the whole screen, and I need to share the screen now. And is this visible? Charlie, are you able to see the screen? No.
I cannot see. I can see you. I can see you. I cannot
Okay,
see
okay,
the
okay.
slide.
Right. How about we do it from here? So slide number 14. There you go. I think this should work.
Okay, thank you. Apologies
Great.
for that. I'll try
And
to go faster, a bit faster through this
sure.
section. So
Are you
basically,
able
I was
to
talking
are you
about.
able to move the slides as well from below? There's a slide counter at the bottom. Do you see anything like that?
Yes, I can do that. Yeah. Okay. Perfect.
Brilliant.
Yeah.
Okay.
Apologies also for the resolution of the slides. I think I printed in low resolution to be able to send it. Anyway, I'll
That was great,
continue.
actually.
Apologies for these technical delays.
Could
So
I
yeah, I
also
was
say,
talking about.
I'm sorry, Jordi, apologies. Could I also say that it might be that sometimes the conversion of the PDF to this, to the Blackboard style causes some challenges in the resolution and the font size. So please don't worry
It's
if
okay.
it comes up like that. I'll share the PDF as well. Thank you.
Okay. Thank you so much. Thank you. So I was talking about the 1D formulation, so 1D 0D modeling that allows us to simulate pulse wave signals and the effect that those signals have, the propagation of the pulse waves has on blood pressure, blood flow, and other hemodynamic properties. And now I'm showing you what our efforts really to verify that the 1D 0D formulation is a good approach, right? A good approach to simulate pulse wave propagation. And first, what we did to verify the accuracy of the 1D formulation was to do a comparison against experimental data. So in the center, you can see a plan view schematic of the experimental setup that we used. That was a 1-to-1 scale model of the larger arteries of the systemic circulation made of silicon tubes. They were connected to a pump to simulate the left ventricle and then to outflow boundary conditions. And unlike in the human body, here we could be really as invasive as we wanted, and we could measure all the parameters, the input parameters of the model, except for basically we didn't measure the density and the viscosity of the liquid that we used to mimic the rheological properties of blood. But apart from that, we measure all the other properties and inflow and also all outflow boundary conditions. And we got really good agreement between simulated and in vivo, and experimental data. So experimental data, you can see it in two locations in the model, and in solid line, and in dashed lines you can see the simulated approximation, the predicted pressure and flow with time at those two locations. We got root mean square errors smaller than 3% for pressure and a bit greater for flow rate. So that was our first attempt to verify the 1D formulation. Then the second thing that we've done is to also check the accuracy of the 1D formulation by comparison against three-dimensional data provided by a three-dimensional model with compliant vessels. So here the idea was that we wanted the 3D at the bottom and the 1D on the top to be as similar as possible, so they share identical inflow and outflow boundary conditions, the same constitutive law, and then the 1D model actually had the geometry that was obtained from the 3D geometry by taking the center line of the 3D geometry. And so then we were able to compare again 1D versus 3D, flow on the left and pressure on the right with time. And yeah, we got average relative root mean square errors smaller than 3% in both pressure and flow rate along this idealized model of the full aorta. And then the next thing that we did is also to test the accuracy of the 1D formulation, again by comparison against 3D modeling, but now with models in which there were aneurysms and stenosis, so localized changes in the cross-sectional area. And yeah, again, we obtained a bit higher errors in root mean square, higher errors between pressure and flow, but again, I think they are still reasonable given the high computational cost of 3D modeling. So that requires using high performance computer and running simulations for hours, if not days, compared to just running the simulations in 1D modeling on a laptop for just a few minutes. We have also done some verification against in vivo data, and we did that by acquiring the geometry of the upper thoracic aorta of volunteer using magnetic resonance imaging, and then by measuring flow rates across several positions in the aorta, and also measuring changes in the luminal cross-sectional area. And we could also measure pressure by tonometry. And this is the sort of agreement that we got. And here we tried to have as many parameters as possible, patient-specific or volunteer-specific. And yeah, again, all the parameters were calculated from the input data, except for the density and viscosity of blood. And also the 3D solution, so using full 3D blood flow modeling, provided very similar results to the 1D solution. So these verifications give us confidence in using 1D modeling to simulate pulse wave propagation in the arterial system. And the next thing that we've done with 1D modeling is to generate these data sets of in silico simulated pulse wave signals for thousands of virtual subjects. So I'm gonna start by explaining a bit the rationale behind our motivation to simulate these data sets. So the idea here is that developing and testing algorithms and indices to assess pulse wave signals requires comprehensive data sets measured in large clinical cohorts. But unfortunately, acquiring these data sets is usually a complex task. And on the left, you can see some of the issues that we may encounter. And to facilitate this process, we have created data sets of simulated pulse waves representative of samples of real subjects using computational blood flow modeling. And here you have the main steps of the methodology that we have developed to produce these data sets. So there are these 5 main steps, and I'll go through each of one in detail now. So the first step consists of simulating a baseline virtual subject at 25-year-old. And we could do that really with existing data from the literature. So those are the arterial segments that we simulated in the middle. And then we could simulate blood flow, blood velocity, luminal area, and also the photoplethysmography signal at several positions in the body, at common measurement sites in the human body. The PPG signal, I'll get back to that in next slides. It's really important because it can be acquired by wearable devices. So that offers really possibility to assess pulse wave, to acquire pulse wave signals in daily life, and therefore to assess cardiovascular health in daily life. So that's the first step. So we simulate a baseline subject, so just one virtual subject. The next step is to really do a review of the clinical literature to really understand how each input parameter to the 1D formulation changes with aging. And so here you have all the input parameters that we look at. So basically all the parameters that we need for the 1D formulation. And in solid lines, you can see the mean value of the parameter for different ages. And then in dash or dotted lines, you can see plus and minus and 1 and 2 standard deviations from the mean. So that gave us a good idea on how to change parameters to really simulate a big data set of subjects. So the third step consisted in understanding really the effect that each parameter, when changed by plus or minus a standard deviation, has on the simulated signals at different arteries in the body. So for example, the carotid and the radial arteries, as you can see here. And we obtained basically that there were 6 input parameters that had a significant effect on the morphology of the pulse wave signals. So that was those were the parameters that then we used to generate a big data set of subjects. So the next step consisted in simulating baseline subjects at 35, 45, up to 75-year-olds. And we did that by considering the mean values for all input parameters that we obtained from our clinical literature review. So that gave us already 6 virtual subjects. And then to get really a population of thousands of subjects, what we did is for each age group, what we did is to simulate a pulse wave for a set of subjects by changing the 6 cardiovascular properties that we identified in step 3 as being really producing significant effects on the pulse wave. And we did that by changing by plus or minus 1 standard deviation from their age-specific mean values. And we accounted for all possible combinations, and that gave us about, I think it was over 700 subjects for each age group. And then because we have 6 age groups, so we had over 4,000 virtual subjects. So once the data set is created, then what we did is to verify that the simulated pulse-wave signals were representative of samples of real subjects. So we did that by comparing simulated pulse wave with in vivo data from healthy subjects from the clinical literature. And here you can see comparisons in a few arterial locations showing similar changes in pulse wave morphology with age to those measured in vivo, including also for the PPG or photopulsatography signal measured at the finger. And we also did actually comparisons of pulse wave indices between the simulated and in vivo pulse wave. And quite remarkably, actually, we found that simulated pulse wave indices and shapes from aortic root to digital artery compare really well with in vivo data across different age groups. And now that we have this methodology to generate these populations of in silico pulse wave, then what I want to show you is some applications. So why is it useful to use this in silico data to do research in hemodynamics? So this is what I'm going to show you for the remaining of the talk. And the data set can help us with the 4 bullet points that we have here. So it can help us design and test algorithms and indices of pulse wave analysis, including machine learning models. It can help us understand the potential shortcomings of existing technologies and also understand the mechanisms underlying hemodynamic observations. And we've carried out lots of studies using in silico testing. So here there's a summary of those studies. I cannot go in details through all of them. Today, I want to focus just on 2 of them, perhaps only one, given that we are running a bit late. The first study is the detection of abdominal aortic aneurysms, or AAAs, from pulse wave analysis. So these aneurysms are usually asymptomatic until rupture, which is unfortunately associated with very high mortality. Therefore, early detection of AAAs is really of paramount importance in reducing mortality. But here the problem is that most AAAs are detected by medical imaging incidentally. So we are investigating pulse wave analysis methods based on machine learning that are more convenient but also less expensive for large-scale screening than medical imaging exams. And we have created a machine learning architecture that is based on the recurrent neural network to actually detect AAAs from the PPG pulse wave, so the photoplasticography pulse wave that can be acquired by wearable devices. And our method was trained and tested using this PPG signal measured at the finger from a data set of over 10,000 virtual subjects with and without AAAs. Yeah, and we simulated AAAs simply by changing the geometry of the abdominal aorta. And the model had a very high sensitivity and specificity in early detection of AAAs, as the confusion matrix and receiver operator characteristic curve show at the top. Remember, this is in silico data, so we are getting really very high sensitivity and specificity. But then what we wanted to do is to simulate a more realistic scenario during testing by adding random noise to the PPG pulse wave. And that reduced the sensitivity and specificity, as you can see at the bottom. So we got still above 86%, but it's much less than before. But this still suggests that the trained machine learning model is competent in classifying normal and aneurysm conditions using a digital PPG pulse wave that has really less resemblance to the pulse wave of the training set. So the In Silico data set seems to be useful when it comes to the design and also the testing of machine learning models. Other clinically relevant application that I want to show you, I think there's a bit of time still. Otherwise, let me know, but I'll continue otherwise for 10 minutes or so, is the estimation of the stiffness of the aorta, so aortic stiffness, which is an important marker of vascular health. So indeed, increased arterial stiffness has been shown to be an independent predictor of morbidity and mortality from cardiovascular disease. Aortic stiffness cannot be directly measured in vivo, but we can use the velocity of propagation of the pulse wave, so the pulse wave velocity, as a surrogate for aortic stiffness. As an example, the plots show that the probability of overall survival on the left and event-free survival on the right decreases considerably with the increasing pulse wave velocity in a cohort of end-stage renal disease. So pulse wave velocity really can predict these probabilities. And in fact, vascular assessment and the related vascular age of your arteries is really an important topic. And there is now this Vascular Age Network. It's a cost action by the European Union that focuses on this topic. And actually, we are participating. We are leading the physiological and technical background working group, which is one of the 5 working groups of this cost action. There are several clinical methods. So this pulse wave velocity is measured in the clinic, and there are several methods to do that have been proposed to measure pulse wave velocity from pressure and blood flow waveforms measured at 2 arterial sites. For example, the arterial sites that are shown in the sketch on the left. And typical combinations of waveforms are shown in the center. And the sketch on the right illustrates the foot-to-foot method for estimating aortic pulse wave velocity using 2 pulse waveforms. The method calculates pulse wave velocity as the ratio of the distance between the 2 measurement sites to the time delay for the foot of the pulse wave to travel from one measurement site to the other. So distances are typically measured from surface markings and time delays by identifying the feet of the 2 wave using pulse wave analysis. And we have actually assessed the accuracy of these methods using a population of over 3,000 virtual subjects. And our results really show that only the carotid femoral pulse wave velocity is a good indicator of aortic stiffness, which is also in agreement with clinical studies. We could also provide in our study using In Silico data a mechanistic explanation of why this is the case. So results on the left show that the carotid femoral pulse wave velocity, so the method used in clinical studies, usually as considered to be the gold standard method, correlates well with aortic pulse wave velocity across a wide range of values of the true aortic stiffness, which we really know in our In Silico models. However, on the right, we can see that brachial ankle pulse wave velocity overestimates aortic pulse wave velocity, since it is related to the stiffness and also to some extent to the geometry of more peripheral muscular arteries than the aorta. And also we saw in our study that carotid radial and also femoral ankle pulse wave velocity do not capture aortic stiffening. And they are therefore not so good surrogates of aortic stiffness, which is also in agreement with in vivo studies. These methods tend to capture more the stiffness of peripheral vessels, but not the aorta. And the carotid femoral method is an accurate method that is widely used in clinical research. However, it requires skill operators to acquire the data. And that means that the applicability of the method is limited to the clinic. So using a combination of in vivo and in silico data, we are investigating methods to estimate pulse wave velocity from a single pulse waveform. So those are single point methods. And the idea here is to use pulse wave analysis to identify fiducial points on the waveform by calculating first, second, and even higher order derivative of the measured pulse wave signal. And then we can calculate indices from these fiducial points. So basically, we do an analysis of the morphology of the signal, of the pulse wave signal. And we have shown strong correlations with aortic pulse wave velocity of indices calculated from pulse wave morphology. However, so apologies for that. So, however, we've shown these strong correlations that you can see on the screen between at least these three indices of a stiffness and true aortic stiffness. But what is important to realize here also is that these indices are influenced by other cardiovascular properties, such as heart rate and stroke volume, and also the diameter of arteries, which may affect their ability to stratify patients. Apologies, I'm missing, when I made the PDF, I'm missing a slide here that shows how we can actually quantify this effect of other cardiovascular properties on these indices using in silico testing. We can do that really, and we can then provide a mechanistic explanation of why, for example, the third index is performing better than the other two when it comes to stratifying subjects within an age group. So all the indices perform well for when it comes to stratify subjects throughout the 25 to 75-year-old, but only the last one stratifies well for one age group, for example, the 45-year-old subject group. And yeah, now that at the moment what we are doing, and we've already published an article on that, is to use machine learning to estimate pulse wave velocity. And here the approach is to use either fiducial points, so the fiducial points that I explained before that can be calculated from first, second, or higher order derivative, or just providing as an input the whole waveform, so the array of pulse wave magnitude points to a recurrent neural network with long short-term memory. And for this study, we had data actually from Twins UK, so it's a cohort from King's College with over 3,000 subjects for this study, in which we had the radial pressure waveform together with the carotid femoral pulse wave velocity. And then we also use a data set of virtual subjects, of over 4,000 virtual subjects. And these are the results that we obtained using the first approach on the left, in which we use as an input fiducial points of the pulse wave. And on the right, we have using the recurrent neural network. So that means just putting as input the whole morphology of the pulse wave signal. On the top, you can see a scatter plot comparing the estimated on the y-axis and the measure on the x-axis. And then at the bottom, we can see Bland-Ullmann plots. And we got these average root mean square errors smaller than 2 meters per second, which perhaps it's not so good, yeah, when it comes to estimating pulse wave velocity. But remember that this is done just from a single measurement of the pulse wave. And then because we got these high, well, perhaps not so small errors, then we wanted to use the virtual cohort of patients to understand if that could be because of noise in the input data. And actually, what we did is with the simulated in silico data is to artificially add noise to our signals, and then we observed that the error of the machine network model actually increases with obviously added noise when you do the training, the testing. Sorry, but in any case, we we think that this in silico testing and actually training of machine learning models could be helpful, at least to give us the smallest error that can be achieved in the estimation of pulse wave velocity in this case under idealized conditions, and then add control error in a controlled way to see how that might affect the solution. And yeah, and actually, with that, I would like to conclude. So we have seen that pulse wave signals, including the PPG signal, can be modeled accurately and efficiently using computational platform modeling. In silico datasets provide a quick and inexpensive route to do initial development and assessment of pulse wave analysis algorithms and indices. And we can do that across a wide range of cardiovascular conditions and in a relatively quick and inexpensive manner. And lastly, in silico testing enables us to understand physical mechanisms underlying correlations observed from populations of subjects, and also train machine learning models also across a wide range of physiological conditions. And they may also be useful for interpretability of new network models. And moving forward, the combination of in silico testing with machine learning and the fact that these wearable sensors are really proliferating a lot and lots of people seem to use them, provides new opportunities for assessing cardiovascular function within the wider population using pulse wave analysis. So I would like to conclude here and to thank my group and funding bodies, which have all contributed to this research to some extent, and so collaborators. And I'll thank you for your attention and apologies for the technical problems.
Thank you very much, Jordi. It was a fantastic presentation. Really enjoyed it, and took us through a very nice journey, starting from verification of the. I think your models are just as much accurate. Let's say sophisticated as they need to be for the purpose of, and then a lot of different novel applications even. So I would open the chat forum. So if you have questions, please feel free to put in your questions in the chat. And Jordi, I also apologize for the technical problems, but I think we made it in the end. So it worked quite well. I have one question while people are putting in their questions in the chat box. The question was related to, when you, I think we got to step 1, 2, 3, 4, 5 in the very beginning. I think it was step 3 or something, where you said that of the very wide, diverse range of parameters that there are in the model, you reduced it, please correct me if I'm wrong, to those to which the output is more sensitive. So in doing these, did you observe like any interaction effects or nonlinear effects? That could probably be important for either populations who have disease or populations with different ethnicity or very different kind of age group perhaps, which
So producing the data, we to understand whether all parameters had a significant influence on the morphology of the stimulated signals or not. And also, I said, also paid attention that some parameters are related to each other. So, for example, stroke volume and heart rate are related to each other. So we took that into account. So I had a very good postdoc doing this project, who is now in Cambridge doing a VHF fellowship, and he actually went through over 100 clinical papers to really understand input parameters the values of those input parameters from real clinical studies, so in real clinical populations. Obviously, you need to go through lots of papers because each paper gives you maybe just one parameter or a couple of parameters, and it tells you how those parameters change with aging. But also for each parameter, we look at more than one paper, more than one clinical study. And yes, we saw when doing the literature review that there are these interactions between parameters, and that those were taken into account. Yes, also when generating the population. Yes. But obviously, then the critical moment is when you do the testing, right? Because the testing, remember that here what we are doing is we simulate, and then we get the simulated signals, and then we treat them as if they were real signals. We calculate indices as you would do in real signals, in vivo signals. And there are also other papers in the literature that have observed how these indices in real populations, how they change with aging. So then we also compare our simulated signals and indices, how they were changing with aging. And the agreement was really good, actually. But remember, this is for normal aging, so normal physiological conditions. So there was no disease in here. Yeah. Then we did the study with the aneurysms, in which we added aneurysms into our healthy subjects, yeah? Our healthy virtual subjects, I must say.
So thank you so much, Jordi. And so the next question is from Steve Matchard. I'll just make you present to Steve so that you're able to ask the question. Yes, I think you're able to use your microphone now, Steve.
Yeah, hello there. Yeah, thanks. That was really interesting talk. I just wondered how critical are the rheological properties of the blood in determining these kinds of waveforms?
No, they are not that critical, actually, because what the effect that they have is on the dissipation, so on energy losses throughout the large arteries mainly, and those are really small in large arteries. So, for example, we can run simulations without viscosity, and you get really very similar results. They are more critical when you simulate the smaller vessels, but the 1D formulation, the assumptions of the 1D formulation are not valid for a small vessels, maybe smaller than 1 millimeter in diameter. So yeah, and it's not that critical, but obviously that's why we wanted to do the testing, right? Remember, in the testing, we just we did a measure, but it's not that we did any tuning. It just we took a value for the rheological properties, so basically density and viscosity of blood from a textbook, from a hemodynamics textbook, and they don't have a big effect really. At least when it comes to the propagation of the pulse wave and the effect that has. Yeah, of course, yes.
So my follow-up question would be with the optically based PPG sensors, they tend to use radiation of quite a short wavelength. Is there any risk that they are more skewed towards looking at those small vessels?
Yeah, okay. So
you don't have the penetration to look down into the big ones.
Yeah. But here I didn't explain how we simulate the PPG signal. And the way that we do it, and also, at least to me, I don't think it's clear yet what's the origin of the PPG signal, right? Completely clear. It seems to be related to the pulse wave. The way that we simulated the PPG signal is from calculating blood volume in the peripheral vessels, and then calculating that as a function of time. And that's how we simulated those signals. And then we normalize, right, so that the signal goes from 0 to 1. And yeah, and then we compare those simulated signals this way, yeah, with data from signals from the real literature, from in vivo signals, yeah, from the clinical literature.
Yeah,
but
I guess it's quite a critical part of the whole story in the sense
signal,
yeah. You're hoping to use the PPG
yes,
signal
to of course,
perform the diagnosis of things like the AAA. So
yes,
my comment is that's probably quite a critical point.
Well, but it's not critical in the way that we've done to simulate the signal, yeah, because It's from
No,
changes
but,
in
no,
blood
but
volume.
in the real world.
Yes, yeah, in the real world, yes. But in our simulations, so when we compare with real data, and we are not doing this patient specifically, it's more population specific, right? The comparisons that we are doing. Yeah, I accept that. But yeah, that's what we are doing. So I'm just reporting what we are doing and the results that we are getting. Yeah. To me, the limitation here in what we are doing is the fact that we are simulating only one cardiac cycle. And you know that when it comes to PPG, it's very important also to look at variability, right, throughout different beats, yeah, cardiac cycles. But in 1D modeling or even in blood flow modeling in general, it's not done really, the simulation of multiple cardiac cycles. Perhaps in 0D modeling, yes, you can do that. That's one of our aims for the future, to simulate dynamics, right? So the effect, for example, of respiration, yeah, on the simulated signals and other systems of the body. Yeah, I think this is more critical, I think, to me, when it comes to wearable devices and doing pulse wave analysis, yeah, from some signals that you can acquire by wearable devices. Yeah.
It's an interesting point you raised, Jordi. I think one of the questions is that how does having this virtual data set, does it help you in, let us say, predicting disease early, like picking out biomarkers of any potential diseases early?
Yeah, well, there is already clinical research using pulse wave signals, and the example that I've provided is vascular function, right? So vascular aging. This carotid femoral pulse wave velocity method is really used in clinical studies. And also I mentioned the cost action network, Vascular Age Network. And we are very active, and there's lots of interest across Europe in understanding how to measure, how to quantify vascular function. And yeah, and that's, it's not using, well, you can use PPG signals, but also usually it's done at the moment using blood pressure signals. Yeah, you can also use Doppler, so also blood flow velocity, and tracking the diameter, changes in the diameter of the arterial wall. Yeah. But there is lots of research really being done in analyzing pulse wave signals in vivo. And the idea here, we come from modeling, right? So we try to help with this in silico modeling, right? To try to understand also mechanisms, yeah, understand mechanisms. Even what we would like to do is to do the training of machine learning models using in silico data, maybe with a bit of in vivo data, and then do the testing using in vivo data and see and prove, right, that these in silico data sets can help with the training, and then can be used in real data. Yeah, when so that would help, I think. But yeah, we haven't done that yet. Yes.
Thank you, Jordi. Thank you, Steve. Is there any other question? Let's see, chat box. No, not yet. All right. Okay. Well, I just also realized that the hour is coming to a close. So if there is, so I think it was quite a really nice presentation once again. So thank you very much, Jordi, for and for the patience with all the technical difficulties that I created on the side. So once again, thanks very much, and it was great having you here, and I hope to see you sometime here physically.
Yes, yeah, the same goes for me. Yes, thank you very much for the invitation. Yes.
All right. Thank you, everybody, for coming today. And this session, as I said, will be recorded and will be uploaded. And I will share the link with you, Jordi, as well. Awesome. Stop the recording.